Okay, I'm now recording. Man, what is up with my computer? Let's go. Come on. I think my computer is telling me it's time for a new computer. I know, but I guess it's time for a new one. Okay, go ahead and click in for attendance. Everybody good? Okay, my computer looks like it's decided to come back. All right, so last class we were talking 4-3. We got to finish 4-3, do 4-5, and then we can talk about the exam. So in 4-3, what we were learning how to do was graphing quadratic functions, and I gave us a set of steps in order to do that, A through F. And we did one or two of them, but we hadn't done this one, right? So I'd like to go ahead and work through this problem, and then we'll move on to the last topic, or last two topics in this section, and we'll be ready to move on to the next one. So what we're going to be doing here is trying to sketch the graph of f of x equals 3x squared minus 8x plus 2. And the steps were, first, anyone remember? Make sure you identify that this is a quadratic function, which it is. Step B is to determine if it opens up or down. So it opens up. We know that because A is 3. Anytime the A is a positive number, it opens up. Part C is to find the vertex. And we have a couple of options for the vertex. If we're given the function in what's called expanded form, which is what we're looking at here, then we had completing the square, or we had the shorter way, which was that formula. And I think everyone liked the formula, so I think that's what we'll use here. Remember this formula to get h and k? H was negative b divided by 2a, which for us would be, what's negative b for us here? Positive 8 over 2 times 3. So this is 8/6, which is 4/3. And I'm going to leave it as a fraction. So that's what the h is. The k is what I get when I take that answer, 4/3, and I evaluate the function there. So I plug it into the function. So I just need to be careful here. It's 3 times the 4/3 being squared minus 8 times the 4/3 plus the 2. And we try and work this out. So let me square. What the hell's that? No, I don't want that. I square 4/3, so square top and bottom. This gives me 3 times 16/9 minus, now on the 8 times the 4/3, I just go 8 across the top. 8 times 4 is 32 over 3, and then plus 2. And I believe I can do some reduction here. This 3 is like a 3 over 1. So I can do like 3 goes into 3 once, 3 goes into 9 3 times. I could do that. You could multiply across and reduce the fraction. Whatever you're most comfortable with. What would I be left with here, though? 16 over 3, and then take away 32 over 3. And I'm going to have to bring that 2 into play here, right? So why don't we just write that with a common denominator of 3? So 2 can be rewritten as 6 over 3. And now we just combine all the numerators. 16, take away 32, add 6, all of that over 3. We get negative, this is negative 16 when you put those together, and then add 6, so negative 10, negative 10 thirds. Just leave it like that. So our HK for this problem is the point 4 thirds, negative 10 thirds. And if you needed to put that as a decimal to help you graph it, you can now get on your calculator, do 4 divided by 3. You get what, 1.33333 forever. Then if you do negative 10 divided by 3, you get negative 3.3333 forever. I'm just going to round it off. And now we move to the next step. Any questions? What is the next step? X-intercepts. You find so you do a quick sketch, and then you see if you have X-intercepts, right? So I'm going to do a quick sketch on this one. I'm on part D. The most important thing with your quick sketch is to locate the vertex. So the vertex, I move to the right 1.3, and then I move down 3.3. So my vertex can be somewhere in this area, and my parabola opens which way? What did we say from part B? Up. So if this parabola opens up, do you agree that we will have 2 X-intercepts? Since we have 2 X-intercepts, I need to find them. And to find them, what do? Set the function equal to 0, right? So you set 3x squared minus 8x plus 2 equal to 0. And I heard quadratic formula. You could try factoring. I don't believe it's going to work. So you have to use a quadratic formula. So when you're looking at my solutions to things, if you see me write QF, I mean quadratic formula. And then you just apply the formula. Do you feel like you would need me to supply you the formula for the test? Or is that something you have memorized? Yeah, I don't really have a problem supplying you with the quadratic formula. So negative b plus or minus square root b squared minus 4ac all over 2a. All that junk, right? So putting this all together, I'm going to go over here. The answers will be, see, 8 plus or minus square root. Let's figure out what this is. I like to do it this way. 4 times 3 is 12, times 2 is 24. But then I'm going to be taking it away. So when you take 64 and you take away 24, what are you left with? 40. So I have square root of 40 all over 6. Now get on your calculator, do the square root of 40. It's going to be about 6 point something. 6 point what? Anybody? Anybody? I'm going to go to the next page. Okay. Okay, so 6.32. Okay, we'll just go that far. All over 6. Now, don't mess this part up, okay? Don't mess up the part of putting these together. You have to first, on your calculator, do 8 plus 6.32, hit enter, and get what the answer is. All right? Then divide by 6. So 8 plus 6.32, enter, divide by 6. Wait, you got what? 14? Okay, yeah, and then divide by 6, and you get 2.38. I wouldn't take off for that. I don't care. 2.38 is good enough. So that's one answer. The other answer, you do the 8, you subtract the 6.32. Divide that by 6. What? Why in the world is my calculator doing this? I lent this to somebody, and then I don't know what happened. .28. Those are your two answers. Okay? Any questions? Y'all good? Two decimal. I mean, remember, we're trying to graph this, so you just, I mean, how accurate can you actually be? Yeah, I mean, it would make no sense to go out 5 decimal places here because you can't be that precise when you draw it. Yes? I have a question. Uh-huh. Are you saying your calculator does the quadratic formula for you? Okay, well, that's fine with me. I don't care. Just if it's wrong, then it's wrong, though. You know what I'm saying? Like, there's no work and you have the wrong X-intercepts. Like, that's more wrong than someone who does this and then accidentally put, you know, a 3 down here instead because they, you know, because then I can see where the mistake is. Yeah, you'll get some partial credit if you show your work. Whereas if it's wrong, if there's no work. Okay, so now step E is what? Find the y-intercept, and that's just plugging 0 into the function. So f of 0 is just whatever number is sitting out there in the end, that's 2. It's going to be a point. And then part f is to put it all on a graph. So here comes my graph. Let me start with the vertex. The vertex was at where? 0.3? Was it 1.3? 1.33, and then you went down 3.33. So again, this is where we're just kind of ballparking this thing. 1.33 down 3.33. It's somewhere around here. And to let everyone know, this is where I'm going to put the 4/3, negative 10/3, so everyone knows exactly what the value of that vertex is. Then I'm going to plot my x-intercepts, which were 0.28. I don't know, somewhere around here, 0.28. The other one was, what? 2.3, was it? 2.68? 38. Do I have to scroll up? 2.38. So that's going to be around here, 2.38. And then my y-intercept, which we said was 2, which is here. Remember, you have that axis of symmetry. It's that line that goes right through the middle, so your parabola should be symmetric over that line. So when you draw it, I mean, on the test, if you draw this, I'm going to take off because it's not a V, right? It's a parabola. So it needs to look like a parabola. So you want to do something like, you know, curve it down here. You're going to come up to this point, through that point, and then just try and make it look as symmetric as you can. Let me label that y-intercept of 2. Now, there are some other things I didn't ask, or that we haven't answered on the question. It says graph the function. There's the graph. It says find the domain and range. What's the domain of this function? Negative infinity to infinity. What's the range of this function? Negative 10/3 to infinity. Do I bracket that 10/3, negative 10/3, or yes? Okay, so the range, remember the y values. The y values go from negative 10/3 up forever. The other thing I ask, find where the maximum or minimum occurs. Where does the maximum or minimum occur? We have a minimum at the vertex, right? So where it occurs has a min at what x value? X equals 4/3. The next part of the question on the sheet of paper says, what is the maximum or minimum value? So that's where it occurs. The minimum value is the actual y-coordinate, which is what? Negative 10/3. I just want you to see the difference between me asking you where a max or min occurs versus what the max or min value is. Where it occurs is the x-coordinate. It's the h in the vertex. What the value is the k, or the y-coordinate. Understand the difference between these two? Kind of? It would be, if it says where is it happening, I want the x value. If it says what's the value, think value is the output. Okay, the value is what comes out of the function. So that's your y-coordinate. Okay, that's it. We're done. Nice, good-looking graph there. The next topic that we have is somewhat interesting, I think. Determine the function from the points. So far, I've given you a function. I've asked you to graph a parabola, right? Now what we're going to do is I'm going to say, look, we have a quadratic function that has a maximum value, a maximum at this point. Also, it passes through this point. Find that quadratic function. Tell me what the function is. This is much different than what we've done previously, right? So I give you information about the function, just 2 points on the parabola, and then you tell me what the actual parabola is. So this ties into something that's a little bit more subtle. How many points does it take to define a line? 2 points defines a line, right? How many points does it take to define a parabola? 3. Except if they give you the vertex and one other point. If they give you the vertex and one other point, then you have the whole parabola, which is what we have here. It's hidden in the wording. It goes through this point also. So if you want to have like a picture of what's happening here, if you go to the left 2 and up 6, you have the maximum point, right? That's what it says. And then it says that it also goes through -4, -2. So your parabola goes through here. So you know that your parabola looks something like this. That makes sense? The question is, what is this function? What is the actual function that would draw that whole thing? Understand what we're being asked? Okay, so let's start with this first piece of information. This point right here is a lot of information. What is it? It's the vertex, which the letters we use for vertex were what? HK. Now, if you go back and you remember from the very beginning of this section, we talked about how when you have quadratic functions, they come in 2 forms, expanded form and standard form. The standard form was when you knew what h and k were, right? And we actually do know what h and k are. So what I'm going to do is I'm going to take this and I'm going to rewrite it, and I'm going to replace h and k with what I was given. And I will be close to having my function. I won't be there yet, okay? So let me do that. I'm going to use the fact that I know that all parabolas can be written in this form, where hk is the vertex. Now, using the fact that h for us is what? -2. And k is what? 6. How do I know that? Yeah, what we're given is that the maximum point is -2, 6. Maximum, right? The maximum point is this. That means it's the highest. That means it's the vertex, right?
No, that's going down.
It has to be going down, right? A is going to be negative, correct. But we're actually going to be able to determine exactly what it is. So let me rewrite this. F of x equals, I don't know what A is, except that it's negative. And then I write what? X minus -2. X plus 2. Oh, I should put an X. X plus 2. And then squared. And then plus K, so plus 6. So this is the function. that draws this. There's one piece of information I do not know, right? And that's A. I still don't know what it is. Other than, like what's been pointed out, we know it should be negative. So how much information have we used so far out of what we were given here? We've just used this, right? So how does this point come into play? Well, let me tell you. I know that with any point that lives on a graph, this is the x, right? And this is what comes out once I plug in that x, right? This is f of x. So what I'm going to do now is I'm going to say, look, this right here, this equation has to work when I use this point. In other words, when I replace this x with what? Negative 4, this side of the equation should spit out what? Negative 2. So I'm going to say, now using the fact that negative 4, negative 2 lives on the graph, I know that negative 2 must equal a times negative 4 plus 2 squared plus 6. So I'm replacing the negative 4 in here for the x. I'm replacing the negative 2 over here for the f of x. Do you all see that that's just this line right here rewritten? Right here to here? Okay. Now let's just clean this up. Order of operations. You do this first, that's negative 2. You square it, you get 4, right? So we have negative 2 equals a times 4, which is 4a, plus 6. Now look at this equation. It's a linear equation, right? You have a there. Can you solve for a? Yes. Subtract 6 on both sides. What do you get? Negative 8 equals 4a. Divide by 4. A is negative 2. So remember how we didn't know what a was? We used this point to recover what a is. And now I can write the actual function. So my final answer is, I'm taking this line right here, f of x must equal the a we just found, negative 2, then x plus 2 squared plus 6. There we go. Where? Plus 2. Right here? This, I'm using the point that was given to me in the word problem. The fact that this point lives on the graph means that when I plug in negative 4 for x, this is what the function spits out. So when I go here, I replace this x, right, with negative 4, put those together, and then that gives you this. Does that make sense? It's important to note that the part that I did here in blue, right, the part I did in blue is just what I needed to do to find a. Once I found a, I come back and I rewrite this, right? Because we were almost done here. We just need to know what a was, right? We almost had the function. We used the blue part to get a, and now we come back in here, plug it in. Now we know what the function is. Okay? All right, let's go to the last example. Falling object on Earth. Okay, so it was discovered long time ago that, well, let me ask you. Let me do this demonstration. If I drop, it's going to get kind of loud. If I drop this book and this piece of paper, which is going to hit the ground first? The book, right? Should I do it? Wake everybody up? Okay. All right. So why is it that the book fell to the ground before the piece of paper? So it has anything to do with the weight or the mass or anything? It has nothing to do with the weight, okay? It has to do with the resistance, air resistance. Air has a larger effect on the piece of paper than it does the book. Now, to prove to you that that's true, what I'm going to do is I'm going to take this piece of paper, I'm put it on top of the book. There's no glue, there's no tape. This is not a trick demonstration. I just set it on top of there, okay? And if you believe that the book falls faster because it's heavier, then when I drop this, the book should move and the paper should go behind it because, like, you know, fall slower because it's lighter, right? If you believe that it's because of the weight. So what happened was they fell at the same time. And the reason was because the book is moving the air out of the way. So the air is not impacting this at all. So it's not being held up by the air. So all objects, it was discovered, all objects on Earth will fall to the ground at the same rate, no matter what object it is, all right? If you take air out. If you take air out. Now, if you want to put air into the equation, then it gets more complicated. But that's what people do in physics classes. You start out with the most basic idea first, then you start adding more complications to it until you get it to model the real world. For example, anybody here take a physics class where you do these things called free body diagrams? No? You imagine like pulling something across the ground, and the first time you ever do it, you act like there's no friction. And then later on you add friction. Then the formulas become more complicated. So what we're looking at here is if you were on Earth and there is no air, which I concede, like that's not going to happen, all right? But if there is no air, then everything falls at the same rate, then we should be able to determine no matter where it drops from, I drop a penny or I drop a feather from up here, if they fall together, then I should know where they are at every point in time. And it turns out that the formula, the function that describes that behavior is this right here, where t is a variable here of time. Time is measured in seconds. H of t is the height of the object after so many seconds. V naught, that's the way we say that, V naught is the initial upward or downward speed of the object. I'm going to explain this again in a second. And then H naught is the starting height. So if I take two markers, I don't have two markers. If I take two markers, a blue one and a green one, if they start at the same height and I drop them, they should hit the ground at the same time. Okay, that would mean if I just drop them, let them go, my V naught, my initial velocity is 0 because I'm just letting them go. If I take one marker and I drop it and I take the other one, I throw it up, which one's going to hit the ground first? The one I drop or throw up? The one I drop, right? Because this one's got to go up first and then come back down. So if I throw this up, then this V naught is going to come into play. It's going to be some positive number. If I take something and I drop the blue one, I throw the green one down this time, which one's going to hit? Green, right? So the green one got there first. I gave the green one an initial velocity. If it's downward, the V naught up there is going to be negative. Does that make sense? Okay. Now H naught is the starting height. So, 4 feet, 5 feet, 6 feet. So once you know, if you know where an object started from, if you know its initial velocity, then you can tell me everything about where it is at every point in time. And it is a parabola, okay? Imagine that that's x squared. Imagine that that is an x. And imagine negative 16 is our a. V naught is our b, right? And H naught is our c. And that looks like the standard form, expanded form of a quadratic, doesn't it? I'm glad you asked. What do you think it is? I'll give you a hint. If you're on a different planet, negative 16 changes. That's the effect of gravity. Okay? Negative 16 feet per second per second. It's the acceleration of gravity. You've probably heard negative 9.8 meters per second per second. If you've been in physics, convert negative 9.8 meters per second into feet per second, and that's what it is. So anyways, this formula works with feet and seconds, okay? So here's the problem. Oh, that always happens, that little thing. Yeah. Where is it? A ball is thrown upward from a 200-foot bridge at 300 feet per second. All right, so you're standing on a bridge. You're not going to throw it. Let's say you shoot it out of some, air cannon or something. It's shot up. When it comes out of the cannon, it's moving at that initial speed is 300 feet per second. But as it goes up, right, it slows down, and it comes back and eventually goes past the bridge and hits the ground down below. Yes? So I did a little picture. Okay? So look, here it goes. So you're launching this up. It's going to go up. Now time is going by, right? Time's going by. Eventually it reaches a maximum, and then it starts to actually come down. And as it comes down, it speeds up. I know it looks kind of like it's jumping, but I couldn't get it to be nice and smooth. And then eventually hits the ground down there, right? Yes? Okay, now, I said that this is a parabola. And here's what I mean by that. If you look at your x-axis as your time axis and your y-axis as your height axis, then that ball going up and down can be modeled with this parabola, where this x-coordinate now, the t-coordinate, is time, right? And then the y-coordinate is how high the ball is. And this parabola does a pretty good job of showing you, look, here's where it left the ground, right? Or where it left the bridge. That's the y-intercept of that parabola, isn't it? And then this right here, where it hits the ground, is the x-intercept of the parabola. And then the highest point is just the vertex. And if I know the highest point, can't I also figure out the time it happened? Yes. So we should be able to determine a lot of things about this ball's movement through the air here. Well, there's no air, sorry. Through space using this parabola as a model. All right? I'm going to add one more thing to this. If this were actually done, a real experiment in real time, okay? If it were done, firing a ball with no air, right? So you got to get someone to take the air out of there. Then we're going to learn that it takes about 19 seconds for that ball to go up and down. That's how long it would take, all right? From a 200-foot bridge. So that's a long time. Way up, it's going to come back down, right? Hit the ground. The way I wrote the code to make this little animation happen, if you actually start this and start your watch, it'll take exactly 19.48 seconds for this demonstration to finish. So this is actually like real, legitimate accuracy in terms of time. All right, so, well, yeah, we didn't throw it. So think about this. I mean, this was a ball being shot from a 200-foot bridge. So this is 200 feet here, right? That's a 200-foot bridge. And it's being shot up at 300 feet per second. 300 feet per second, it's moving pretty fast. I'm going to get sidetracked here for a second. What's 300 feet per second per 1 second in miles per hour? So let's just practice what is called dimensional analysis. How do you convert things? How do you convert feet per second to miles per hour? So the first thing you need to do is convert feet to miles. How many feet are in a mile? In 1 mile, oops, there are 5,280 feet. So I put feet down here on the bottom because I want my units, feet, to cancel. There's 1 mile, 5,280 feet. Now I need to convert seconds to hours. How many seconds in an hour? So over here I'm going to say times. I want this to be hours. Or no, I want this to be seconds because I want that to cancel, and I want hours to be down here. You see that because I want the seconds to go away? Okay, so how many seconds are there in an hour? Well, 60 seconds in a minute, 60 minutes in an hour, 3,600 in 1 hour. So what you need to do here, if you wanted to calculate this, is just calculate 300 times 3,600 across the top and divide that by 5,280. That's 204 miles per hour. So that's moving really quick. So you fire a ball up at that speed, it's going to take 19 seconds for it to come back to the ground. We have to still verify that. So let's answer the questions that were being asked. What is the maximum height of the ball? What is that? In terms of my parabola, what's the maximum height? It's the K in the vertex, isn't it? It's the K in the vertex. All right? When does the ball reach its maximum height? That's the H in the vertex, right? When is the ball 1,000 feet high? That means I want to know when the ball, here's 1,000, right? I want to know when it's here, and I want to know when it's here. That's nothing we've done up to this point, all right? And then when does the ball hit the ground? What is that in our graph? It's the X-intercept. right? There's another x-intercept back here, but as we're going to see, it doesn't make sense. That x-intercept's negative time, so it doesn't make any sense. Pardon? We're about to find out. But I just want to make sure everyone understands that geometrically, these all have meaning on our parabola. So do you all agree we need HK off this thing? Yes? Okay. We first need to come up with the function. It was thrown upward 200 feet per second. What's 200 for us in this problem? It's the V naught. Is it positive or negative? Positive, because it was thrown upward. Okay. The bridge has, at a speed, wait, hold on. No, hold on. 200-foot bridge. Sorry, that's our H naught. Sorry, that was my fault. The 300 feet per second is our V naught. Okay, let me write down the function. I'm going to write it the way it appears there. H of t is negative 16 t squared. That will always be negative 16 t squared as long as you're on Earth, plus 300 t plus 200. And what I'm very much interested in is the vertex, right? I need HK. So let me find the vertex. Notice I'm not asking you to graph this, right? I want to know this information. So the vertex, HK, tell me how to get H. Negative 300 over 2 times negative 16. And you'll need your calculator, and you'll probably have to approximate this. 9.375. Let's get K while we're here. That's H of 9.375. Notice I didn't put F of 9.375. Why not? What's the name of this function? H of t, right? So I'm plugging in this into my function, which is H. So you've got to plug that in to this. So I've got to go and do negative 16 times 9.375 squared plus 300 times 9.375. I'm out of room, plus 200. You will get, if you do this, the first thing you get is negative 1406.25. Then you do your 300 times 9.375. You should get plus 2812.5 and then plus 200. So I'm saying that this is this, this is this, and then the 200 is the 200. So put it all together. I'm getting 1606. Anyone else getting that? 1606.25? 1606.25. All right, now let's try and answer these first two questions. The first one, what is the maximum height of the ball? That we said was the K, right? So which one is it? This is it. So I need to put 1606.25 feet. This is the maximum height. Part B says, when does it reach its maximum height? That's the what? That's the 9.375, and that's going to be measured in seconds. And then we're done with part A and B. When is the ball 1,000 feet high? When is it 1,000 feet high? Doesn't it mean this? Doesn't that mean when is the function 1,000? So when is negative 16 t squared plus 300 t plus 200 equal to 1,000? Yes, that's what it means. And then you just move everything to one side, so subtract 1,000 from both sides. That gives you negative 800 equals 0. This is a quadratic equation, and we can solve it using the quadratic formula, right? Okay, so I'm not going to go through all that work because there would be, work that you would have to do there, applying the quadratic formula. I don't feel like doing it. But I will tell you what the answers should be. You should get two answers. And remember, they're not x's, they're t equals, from the quadratic formula, you should get 3.22 and 15.53. And that's measured in seconds. So there are two times when the ball is 1,000 feet high. On its way up, after 3.22 seconds, it goes up, reaches its maximum height of 1,606 feet, 6.25 feet, comes back down, and then at 15.53 seconds, it's also 1,000 feet high. The final question is, when does it hit the ground? So how am I going to determine when it hits the ground? Set the function equal to 0 this time. So this is the last part of this. You set the function equal to 0. Negative 16 t squared plus 300 t plus 200 must be 0. That's the ground. Right? You want your final height to be 0. When does it happen? So again, quadratic formula. And let me just modify this here. You should get two answers. T is equal to negative 0.645, and then the other one is 19.39, something like that. Seconds. And which one of those do I throw out? The negative, right? Because it doesn't make sense to have negative time in this problem. Time started when we threw the ball. So the parabola has no idea that this is a ball being thrown off the bridge, like thrown up. It has no idea. So it's still going to have X-intercepts back here. It's just for us, within the framework of our problem, it doesn't make sense to have negative time. All right. Let's see if you followed that. Let's do a little poll here to see how everyone feels about that. A yay or nay? All right, we are done with this section. Let's move on. Nope, there's one more section. It's pretty short, though. .5. Quadratic inequalities. We've discussed this before, okay? We've actually done this in the very beginning, earlier in the class, and I said we will revisit this. So now it's that time. So we are looking at inequalities as opposed to equations. Inequalities. There are four inequality symbols. Greater, less than or equal to, less than or equal to. Anytime you have a quadratic with an inequality symbol, it is called a quadratic inequality. We should already be familiar with the left side of this. The question is, how do you solve a quadratic inequality as opposed to a quadratic equation? Quadratic equations, we just use quadratic formula or a factor or whatever. That's if it's equal 0. But if it's the inequality, we have to be extremely careful. So here are my suggested steps. First thing, to solve a quadratic inequality is to first solve the corresponding equality. So turn it into an equation and figure out what the answers are. That's the first step. Remember that the solutions to this equation are equivalent to the x-intercepts of this function, right? The x-intercepts of a parabola is when you set the parabola equal to 0. So you need to make that visual connection between these answers and how they represent the x-intercepts of a function. Now, take the answers you have from here and draw them on a number line. We've done something like this before. You get your answers. You know that these are the x-intercepts of your parabola. Then look at A. A being that number that was in front up here. Look at that A. If A is positive, you know the parabola opens up, right? If A is negative, you know it opens down. I'm showing you the example where A opens, where it opens up, right? If I wanted to know where this parabola was greater than 0, I would be saying I want to know when this parabola is above the x-axis, yes? Which would mean everything out this way and everything out this way, yes? If I wanted to know when it was less than 0, you'd be looking inside here. So this is just a quick extension of what we've already done. We're going to do a quick little sketch of a parabola. Quick sketch. We're not even going to mess with the vertex. And then from that, we're going to figure out our intervals where we'd be positive or negative. All right? And that's it. There's nothing more to it. So we're going to do these examples. So the first one, what we would like to do is solve the inequality 4x squared is greater than 16x. Okay, you have to recognize this as being a quadratic inequality. You have a variable in here, it's x, it's squared, it's quadratic. So the first thing we'll do is move everything to one side. We need to make it look like this, ax squared plus bx plus c greater than 0. Or it could be less than 0 or greater than or equal to or less than or equal to, but we need to get everything to one side. So how about I take that 16x over to the left, which means I subtract it. How about dividing both sides by x? Could I do that? Yes. That's if you multiply both sides by a negative. Only if you multiply or divide by a negative, which I'm not because I'm subtracting, so it's addition. If you divide both sides by x here, you may accidentally divide by 0 when you're not supposed to. So always move everything to one side. All right, that's the first thing. All right, so everything's to one side. We happy with this? I'm going to box that in red because that's the thing ultimately that's the thing we're trying to solve. What x's make that true? So what I said to do is convert it to an equality. So take it, turn it into an equation, and solve that equation. How would you solve this equation? You can take out a 4x, so factoring it, what would you be left with if you took out 4x? X minus 4? Everybody agree? Could you set these two factors equal to 0 and give me two answers? What are those two answers? 0 and 4. These represent x-intercepts on a graph, don't they? Those represent the x-intercepts of this parabola. What I'm saying by this parabola is if I were to graph this thing in yellow up here, right? If I were to graph it, I know that it hits the x-axis here and here. So I'm going to go draw that over here. Here's 0. Here's 4. Which way does this parabola open? Up. So I can also tell you that it would do something like that. Everybody agree? And what I'm interested in knowing is when this thing is greater than 0. What does that mean? Positive, right? When is a function positive? It's when the graph is above the x-axis. Not increasing, decreasing. Not what we're talking about. When is the function positive? Above the x-axis. So where's that happening? Over here, right? And over here. What about at 0? What's happening at 0? Well, at 0, it's giving me 0, right? Do I want 0? No, I want bigger than 0. So am I going to include 0 and 4? No. So I'm going to leave these as open holes here like that. The red represents my answer. The red represents the answer. Because the original inequality had greater than, right? Let's just try it. If I plug 0 in right here, what are you going to get? 0, right? Is 0 greater than 0? No. So you can't plug 0 in. Same thing with 4. You can't plug 4 in for the same reason. You're going to get 0 is greater than 0. Now, had there been a little equal sign under here, then yes, we would have included it. Yes. Yes. Okay, take 4x, set it equal to 0, and then just divide both sides by 4, and you get x is 0 still. Yeah.
Why do you change that from open to
Closed.
yeah,
How did I determine that?
yeah, no, like you said first that it was closed out and then it was open.
No, I didn't say it was closed out. I said let's graph our x-intercepts. Let's just see where they are.
Okay.
We're going to determine later if we're going to actually include them or not. So how do I write this answer in interval notation? Negative infinity to 0, parenthesis, union, parenthesis 4 to infinity. Okay, that's it right there. That's the domain. That means for our original problem, right, the original problem as it appeared, which was way up here, if I want to give you, if somebody's going to plug an x in here, it's going to make that true, it's got to come from here or here. If it's not from here or here, this is not going to be true. So what's something that's not in here? How about 1? 1's not in there? So if we plug 1 in here, this shouldn't be true. So 4 times 1, that's 4, and then 16, 1, 16. 4 is not greater than 16. It doesn't work, right? Okay. All right, let's try another one. How about part B, negative 2x squared, what is that, plus 4 is greater than or equal to 3x. So the first thing I'm going to do is recognize I have a quadratic inequality. I'm going to move everything to one side. I'm going to just leave the stuff on the left there, and I'm going to move the 3x to that side with it. So I subtract 3x on both sides, and I put it in descending order. Now, this is the thing that I'll be looking back at, referring to. What do I do with this now? Set it equal to 0, right? And then you try and solve that. Does it work? Can you factor this? Yeah, I don't think it's going to go. So what are your only options? Quadratic formula or completing the square. I think I'm going to go quadratic formula on this. Okay, now we've done the quadratic formula, I think, too many times now. Not too many, but prior to being in this class, hopefully you did enough quadratic formula. You would just have to be careful with that negative, right? On that, your a is negative 2. So just be careful with that. It's negative b, so it would be 3 here. B would be 3. Or negative b would be 3, sorry. Okay, I'm getting from the quadratic formula 2 answers. And I'm going to have to round them. Negative 2.35, and then the other one is 0.85. Those are my 2 answers. So that would have taken a little bit of time to get. And now I do a quick sketch. I plot these points. Here's 0.85. The other one was negative 2.35. I know that these are x-intercepts of that graph. Which way does this graph open? Down, right? I'm looking back at this. I'm looking at the left side as being a function, a parabola. The a is negative, negative 2, so it opens down. So I know it looks like I totally missed it. And what am I interested in? Where this thing is positive, or it could also be 0. So this time, it's the in-between here, right? Because that's where the graph is above the x-axis. And I do want those two endpoints this time. So solid, solid here. So everything between these two, right, will work. How do I say that in interval notation? Bracket, negative 2.35 to 0.85, bracket, done. Okay, I think I'm going to move to the next example. Not the next problem. I'm going to just leave this. Let me just give you a hint on this if you're going to work it on your own. For this one, just distribute the 4 through first, and then move everything to one side. And it goes exactly the same way. The parentheses is here just to throw you off. All right, so let's see some domain problems. This is definitely something you're going to see on the test, all right? Finding domains of these functions. So let's start with that first one. Find the domain of this function. F of x equals square root of 4x minus x squared. So do you remember what we said when we had square roots and we talked about domains? This under here, which we called the radicand, had to be greater than or equal to 0. So that meant we took this radicand and we wrote it like this. This radicand, whatever the hell it is, has to be greater than or equal to 0, right? Well, now, forget all this. What's in green? A quadratic inequality. You see? I mean, the problem of finding the domain of that function breaks down to really just solving this quadratic inequality. You can solve this quadratic inequality, you've answered the question of what the domain is. Understand? So let's go ahead and do this one. I first turn it, let me write it in descending order first. That's the thing I'm interested in. I'm going to write it as an equation now. So as an equation, then what can I do with this equation to solve it? You could use quadratic formula. It'll go a little easier, though. Factor out. What do you want me to factor out? X. Okay, if I do X, I got to be careful. What's still here? Negative X plus 4. Now, you could have pulled a negative X out, all right? But that's what was instructed, so that's what I did. I set this to 0. That's going to give me one answer. And just be careful with this. Negative X plus 4 equals 0. That means X is what? 4. So we get our two X-intercepts. I draw a quick picture. I plot these, 0 and 4. I have a parabola that opens which way? So go back up to this right here. It opens down. I have a negative in front of the x squared, don't I? This thing opens down. I want to know when it's what? Greater than or equal to 0. That's going to be everything inside and the endpoints, including them, right? Yes. Because it's okay to be 0, isn't it? It's okay to take the square root of 0, isn't it? So it's okay to have the endpoints. What is the square root of 0? 0. That's your answer right there. That's your domain. You could put X as an element of. I wouldn't take off on the test if you don't. Yes, you could put, yeah. Yeah. Yes, question? No? All right, let's look at the next example here, right here. So the domain of this one. We're almost done. g of x is x over the square root of 9x squared minus 9. Bless you. Again. Okay, tell me about this. Domain. What's the domain? So what am I going to have to look at? Okay, good. There's a subtle little difference here, isn't there, than the previous one? The square root, it's okay to have a square root, a 0 in a square root. By itself, right? We just did that in the previous problem. It's okay to have 0. But in this problem, if we get a 0 down here and we take the square root of it, that gives us 0. But then we're trying to divide, right? So we need this radicand to be a little bit different than the last one. Can't be greater than or equal to 0. It just has to be greater than, strictly greater than. So that's the subtle difference. I hope you see that. So what I'm going to do is I'm going to take this and I'm going to say this must be strictly greater than 0. So I don't accidentally divide by 0. Because it can't take a square root of a negative number, right? And it can't be 0 because we would get division by 0. Right? If this whole thing was 0 down here, we'd be trying to divide by 0. That's right. Like the previous problem, this one was not a fraction, right? So we didn't have to worry about it being 0. Yeah, the denominator, if it's in the denominator, that's what we have to be concerned with. Okay, well, that's a quadratic inequality, right? You could solve this. So set this first as an equation. And then how would you do this? Factor 9? All right, that's fine with me. Now what? Yeah, that's what I would do. X squared plus 1, x squared minus 1 equals 0. This x squared minus 1 is this, right? Difference of squares. And now you set all 3 factors to 0. Your answers are 9 is never 0, so you just throw it out, right? X plus 1 gives us negative 1 as an answer, and then here, positive 1. So we have 2 x-intercepts at negative 1 and positive 1. I have a parabola that opens which way? Coming back up here, 9, right? Up. What? It goes up, right? Because this is our parabola, this is the A, right? So it goes up. And we wanted to know where it was what? Strictly greater than 0. That means above the x-axis. So that's going to be, don't include negative 1, but everything out here. Don't include 1, but everything out this way. How do I say this in interval notation? Negative infinity to negative 1, union 1 to infinity. Box it up, and you'll be done. Any questions at all? Now, the last example here refers back to that bridge problem, the ball being thrown on the bridge. A ball is thrown upward from a 200-foot bridge at a speed of 300 feet per second. Same exact problem, right? When is the ball higher than 1,200 feet? So what does that mean? Sorry, I heard it. What? Greater than 1,200. So what we'd be saying is this. When is our height function greater than, not greater than or equal to, right? Greater than 1,200 feet? What was the height function again from that bridge problem? Negative 16 t squared 300t plus 200 is greater than 1,200. That's what this problem breaks down to be. This is what type of problem? It's a quadratic inequality. How do we do it? Move everything over to one side first, right? So you would get this. I'm not going to go through this whole thing. I just want to get this one step done. Subtract 1,000. That's what we're interested in looking at. So now you set it equal to 0, right? You use a quadratic formula, you get your 2 points. Right? You get your 2 points. You draw your parabola which way, up or down? Down, and then you want to know when it's strictly above 0, so you will not include those points. It should be stuff in between. So let you do that on your own. Any questions?
We need to, in this part of the 4.3, we do need to sketch the graph for these kind of questions.
For
the ball.
No, well, in the ball problem, I did not have you sketch anything, right? I didn't, but on the review, I think I may have. I don't know. We'll look at the review right now. Okay, that's it. That concludes everything as far as all the material that will be on the test. Now let's look at the review. So how about this one? Did y'all have any questions on this one? For those of you who've, let's take a poll. There's no harm in telling the truth here. All right. Please tell me whether or not you've started to work on the, if you've done at least half of the review. Okay, yes or no? I'm not showing the results on purpose. Okay, so let's see. Uh-oh. Okay, so you got 48 hours. 44% of you have 48 hours to get this all squared away. So I wanted you to come in here with some idea, with questions, right? I'm asking now if there's anyone who has questions on this. The solutions to all this are posted, right? Let's see if I have it right here. I have not gone through these to double check them, and I was outside sitting in my garage, and it was, you know, I wasn't really paying a whole lot of attention to what I was doing, so could be an error in here. Yes.
No, I just have a question. How, I'm confused in how we differentiate about the local maximum and absolute maximum.
Okay, so local maxes are the highest or lowest points in that area. So this end point right here is a highest point around, right? Like this is the king of the mountain right here. If this is the only mountain, he's the king of the mountain. Now he's not the king of the universe. This one's the king of the universe. Wait, hold on. This one arrow keeps going up forever, right? There is no king of the universe. There's two kings of the mountains, but no. That's a dumb analogy, but does it make sense? Yes. And then it goes for the other end too. The lowest point on the graph is your minimum. So this is a local minimum. Locally, it's the worst student in the class. I mean, you know what I mean, right? It's the lowest point on the graph, locally. Over here, there is no lowest because you see this point right here in the middle? It's not the lowest because there's one next to it that's the same. So there's like a bunch of them that are all the same height. So you can't say that one of them is the lowest. So there's no local minimums here. There's one local minimum here. Globally, right? Is it global or absolute? What do I say on there? Absolute. Global and absolute are the same thing. So this is actually the absolute minimum also because if you look at the entire graph, this is the lowest point. Make sense? Anything else on this? Yeah, you see, that's I put here, and I said this in class. What are the local maximums? The actual local maximum values are 2 and 5. Where they occur, though, are at -6 and at 2. I suggest just put them as points, because the point gives you all the information. It gives you not only where it occurs, but what the value is. So I'll accept the points. If you on this were just to put 2 and 5, I wouldn't take off. All right?
For number 10, it says,
On the review? Okay, let's get to 10. Here we go. It says to sketch these 3 functions. Yes. Go ahead.
one is two sketches because the homework says get the domain, the intercept.
Well, you could be asked for any of that. Yep. Yes. I'm just saying, yeah, I mean, that's a great question. The question's being asked is this is what's being asked on the review, but in the homework, you're asked to sketch and then find domain and range and things like that. And I've said, again, from the beginning of this, right, that I suggest you look at your homework, your class examples, right, because I may ask you to sketch a piecewise function and then ask for its domain and range. I may not, but you should be prepared for it. Which, this, on this one? Like number 2? Or number 10? Where? You want to go to 10? Let me see. Okay, is this the one? Where's that? This?
That's right. The very bottom one is down 1, down 2.
This is left 3, right? Opposite of what you think because it's inside with the x. So that's left 3, order of operations. Now reflection over the x-axis, and then move the whole thing up 2. So I wrote these in the order that they're supposed to happen. Oh, it's down 1. That's down 1, yeah. I must have been, I don't know, drinking. I wasn't, but that's down 1. I drew it correctly, though, right? Okay. What about, let's run through these. Number 2, oh, 7?
Yeah, like I got 3, but X is supposed to be 1/3, and it just kind of have a problem because I tried to do.
See, now you don't. We did this just now, okay? So find the domain of this function. This is a quadratic, right? We have to figure out when that quadratic is bigger than or equal to 0, right? So what we do is we convert it to an equation. Here's the equation converted. Now I rewrite it, first, descending order. Then I find the solutions. Here are my 2 solutions, 0 and 1/3. I know it's a parabola that opens down because of the -6. It's actually here, right? Here and here. And then I want to know when it's bigger or equal to 0, so everything in the middle, because here it's positive, and then I do want the endpoints because it was an equals here. Does that make more sense now? Yes? Anyone else have a question on that? What else? Wasn't there another one on that one? Okay, so look at this one. This one, I give you a square root in the denominator. So you got to make sure that what's underneath it is bigger than 0, cannot be 0, right? Because then you'll have division by 0. So this is what we get. This is not a quadratic inequality, right? That is a linear inequality. Those are easier to solve. All you have to do is isolate x. So I added 15x over. I divided both sides by 15. I reduced the fraction, which means x has to be smaller than 1/3. It could not be equal, or else that would be 0, and then you get division by 0. So how do you say everything less than 1/3? Well, that's the picture. Here's 1/3. Less than is to the left of it. That's the interval. What time is it? Let me. Seems what? Okay, let's run through these, okay? I'm not going to go through all the work. That's why I put the solutions out there. What type of equation is this? Radical equation. You have to be able to solve a radical equation. Isolate the radical, square both sides, solve the remaining equation, repeat the process if necessary. This is an easier problem than the one I gave you on your quiz. The one on your quiz, if you remember, had 2 radicals in it. You had to repeat the process. So you might want to go look at your quiz. Everything's on Canvas. Yep. You know what? Let me go to Canvas real quick because I want to show you. Ew. Whoa, hey, we didn't need that. So I was asked earlier about the videos, like how do you get to the videos? When you go into Canvas and you go to our class lecture videos are here. You click on that, it takes you to YouTube, and then this shows this. You're actually at the class right here. So it's by day, and then by section. You can see I've gotten a little lazy. At first I was saying what the sections were, but now I'm just writing the numbers. Got it? Okay. Now, if you go to Files, that's where you'll find the review and the solutions. Files, let's see, where is it? Exam review and exam solutions. So there's the review, there are the solutions. So you got to be able to solve a radical equation. What was next? What's 3? This is a quadratic type. This is where we had to do a substitution. We had to like squint our eyes and see that that was something special. And so it's a quadratic type. So go back in your notes. We did that. We did problems like that. What's this one? Oh, difference quotient. Know this formula. I don't want to give it to you. But what I'll do is I'll make you a deal. If you can't memorize this, I'll give it to you, but it'll cost you 1 point. Okay? It's only 1 point, but it's still incentive for you to learn it. It's not super complicated, right? So, if you what? You don't want what? I won't give it to you. Yeah. I'm not going to put it on the test, but if you're like, hey, I don't know difference quotient, then I'll come by and I'll write it down for you and I'll take a point off. You know, I was not big at memorizing when I was a student. I could not memorize things. My brain didn't work that way. So anytime I was in a class where I had to memorize something, I'd always just memorize it. And just as soon as the test was handed out, I'd write it down. I mean, that's just what I had to do. Okay, what's next? Probably another difference quotient. More complicated difference quotient. So you need to be able to know, if you get an expression like this, that you need to get a common denominator. You need to be prepared for the algebra required for this. You need to make sure you distribute that negative sign through, because if you don't do it correctly, it's going to mess everything up. Remember, the goal is to get an H to cancel. If that H doesn't cancel, something's wrong. All right, so here's a great problem. I give you 2 functions. They're both rational functions. I ask you to subtract the 2. Well, if you subtract the 2, you have to get a common denominator. To get a common denominator, you got to get, multiply this fraction by something. So we did this in the very beginning. It's like out of the review sections, R4 or something like that, but it's now built into a problem later on in the semester. So make sure you can subtract 2 rational functions and then talk about their domains. I don't know. This is a good idea. This review is a good idea of about how long it's going to be. So again, you need to prepare yourself for this length of exam. This is a quotient of 2 rational functions, so you have to do the flipping. And then remember to always look at your domain before you algebraically simplify. Because on this one, you cancel these, you could lose the fact that x can't be -3. Was that missing something on the end of that? Yes, it was. That doesn't make any sense. It's supposed to be negative infinity. Yeah. We just talked about that. Average rate of change. I will give you this formula. All right? Average rate of change is just a plug and chug problem. You plug in what B is, you plug in what A is into this function, you write down this ratio, and you evaluate it. Just again, be careful with all the signs. Here's the slope of the secant line. Again, this is another formula. That formula look familiar? It's the difference quotient. It's the same formula, but it's different wording. So you're doing the difference quotient, but I'm giving you what X is, I'm giving you what H is, you plug them in to the function, you get your values, and then again, this is just arithmetic, making sure you're following your signs correctly, and you should get some answer. We talked about that. Is that it? Okay, graph this function. So I give you a parabola. That's what we came into class today with. I give you a parabola. I would love to see you do parts A through F. I'm not going to force you to do it. But if your graph looks terrible at the end, I'm going to take off a lot of points because I've given you the structure of how to do it. If you don't use that and your graph is just all off, I'm going to take off more than if you were to follow the process. Yes? You can always use a calculator, right? You want to use two? You can use 5 calculators. I don't really care. I need to see work though. Okay, that's the main thing. I know that all your calculators can graph a quadratic function. That's not the point. I mean, I've actually had people on tests where they draw this on the test, like that's the answer, and they'll draw this. It'll look just like their calculator screen. That's what it'll look like. That's it. That's what they'll put as the answer. There's no other information. Like that's their answer. That doesn't fly. All right. So feel free to use the calculator to check your work. I mean, if I had a calculator, I knew how to graph something, I would. I would do all the work the way I've been asked. And then when I check it on my calculator, it better look something like this. If what I type in the calculator is over here, then I need to maybe go check and make sure I didn't make a mistake. But then you could have also typed it in your calculator wrong, so, you know. Okay, so we did all this. You could be asked for domain and range here. Could. You could be asked where it's increasing and decreasing. You could be asked where it's positive and negative. Right? That's all fair game because it's within the scope of the course. And then, okay, that's the final graph. A ball is thrown upward with a velocity of 200 feet per second from an 80-foot bridge. Same problem we did earlier, different numbers, right? How high does the ball go? That's the K. When does it reach the max height? That's the H. When does it hit the ground? That's the X-intercept. Use quadratic formula. I think there's more, right? When is the ball higher than 100 feet? This is a quadratic inequality. When is it higher than 100 feet? Not when is it 100 feet? And that is all, right? I do have 4 minutes. I know everyone wants to go. Let's just talk last 4 minutes. How are you going to study for the test? Like, what do you think is a good way to study for a test like this? Hopefully you've already done the homework, right? And doing all these review problems. If I were you, I would take that review, if you've written on it, print out a fresh review, write your quadratic formula down on the side, because that's all I'm really going to give you. And then if you need the difference quotient, write that down. Turn off the radio, shut yourself in a room, give yourself an hour and 40 minutes, and see if you can do the review without accessing any notes. If you can do that, you're ready for the exam. If you can't do that, you're not ready for the exam. It's that simple. Now, if you're to the point where you already know how to do that problem, so it's not worth it for you to do it again, you go into your book and you find a problem similar to that problem, and you make your own review with a new set of problems, and you try that same experiment. An hour, 40 minutes, 12 problems, similar to the ones on the review. If you can do that, you're ready. Because you can't expect to walk in here, and that's the first time you try and do those problems in an hour and 40 minutes. If the first time is going to be on what, Thursday, you're putting yourself behind the 8 ball, so to speak. You need to have at least practice that. I remember, I still have 2 minutes. I remember when I did, years ago, I used to do triathlons, believe it or not. And my first triathlon, I was terrified. You know, I didn't know how I was going to do. So what did? I trained. I actually went out to where the triathlon was. I found the routes. I did the entire triathlon the week before the triathlon. And then when I got there, I was so much more prepared for it, right? I was confident because I knew the swim, I knew the hills, I knew everything. Same thing with this. You want to practice test environment. You have to practice that. If you're going and you're doing it, you're like, I got this. You get to a problem, you're like, I don't know. What are you going to do? You don't stop the clock. You move on to the next problem, and then you come back to it, and you try and find where your weaknesses are that way. Okay? Good luck studying. This test is very important. You got to start off on the right foot here. This is our first one, right? First of 3. Okay, good luck. I'm excited. I feel good. I don't know if I should feel good or not. No, I feel good for you. I feel confident that the class is going to do well, but